Hi my dears. In previous class, we discussed about the supremum and the infimum of a set. And we already proved that a set has unique infimum as well as the supremum is also unique. So for example, consider a set of all x fall in R with a 1 less than x less than 2. So here 1 is the lower bound is 1 and the upper bound is 2. And every number 1 or less than 1 is a lower bound, as well as each number greater than 2 is also, a number greater than 2 is also an upper bound. So what is the greatest lower bound? Every number less than 1 is a lower bound, and every number less than 1. So come to the number line, there is a 1. If it is 0, 1, then every number less than 1 is a lower bound. So 1 is the greatest lower bound. Thus, this 1 is the infimum of the given set. Similarly, suppose there is 2. 2 is an upper bound of this set, and every number greater than 2 is also an upper bound. Each number greater than 2 is also an upper bound. So 2 is the least upper bound. So 2 is the supremum of the given set. So this is the infimum and the supremum of a given set x of all in R with the x ranges from, so realizing between 1 and 2. So I consider another set, n, natural numbers, set of natural numbers, 1, 2, 3, etc. Consider this set. So which is a least upper bound. One is not an upper bound, one is a lower bound. One is the lower bound, and every number less than 1, -1, -2, etc. they are also act as the lower bound. But 1 is the greatest lower bound, so infimum of n is 1. What about its supremum? There is no upper bound, so there is no least upper bound, it has no supremum. So infimum of set of natural numbers is 1. Okay. If you consider another set -1, -2, -3, etc. Suppose let it be A. So which is the infimum and the supremum of this set? So -1, -2, -3. -1, 0, -1, -2, -3, etc. So -1 be the, what is -1? Come on. -1 be the least upper bound. -1 be the least upper bound. So supremum of this A, what about the supremum of A? Supremum of A is -1. There is no lower bound, so its infimum is not defined. What about in case of an open interval 0, 1? In open interval 0, 1 means open interval 0, 1, 0 and 1. This is open interval 0, 1. So in open interval 0, 1, what is least upper bound? 0 is the least upper. 0 is a lower bound. Sorry. Yes, 0 is a lower bound. And -1 is again a lower bound. -2 is a lower bound. Whatever may be. So 0 is the greatest lower bound. So infimum is 0. And come on, 1. Open interval 1. So 1 is the least upper bound. So supremum is 1. Infimum 0, supremum. If you consider closed interval 0, 1, what happens? This is a closed interval 0, 1. It includes 0 and a 1. So again, its infimum is 0 and the supremum is also 1. So, like this. Suppose closed open 0, 1. Closed open 0, 1. Half open interval. Here again, infimum is 0, supremum is 1. Again, open closed 0, 1. Again, 0 be the infimum and 1 be the supremum. So, this is the supremum of some nonsense, supremum and infimum. This is the method to find out the infimum and the supremum. If you consider set 2, 3, 4, etc. up to 25. Consider it. Is it is bounded? Then in order to check the set is bounded, first we find out its lower bound and upper bound. This is a lower bound, 2 is a lower bound. 2 is a lower bound. And every number less than 2 is a lower bound. So 2 is the greatest lower bound. So its infimum is 2. Similarly, 25 is an upper bound. And any number greater than or equal to 25 is also an upper bound. 25 is an upper bound. Number greater than 25 is also an upper bound. So 25 is the least upper bound. So supremum is 25. Thus, in case of a finite set, the least element or the smallest element is act as its infimum, and the largest element is act as its supremum. In case of a finite set, the least element or the smallest element is nothing but the infimum, and the highest element is act as its supremum. So this is the infimum and supremum of a set, interval, and so on. Agree? Now let us discuss a lemma. Consider the search. There is a lemma. What is it? Yes, lemma. An upper bound u of a and there is a lemma. Let U be an upper bound of a non-empty set S of R. U be an upper bound of a non-empty subset S of R. Then U is the supremum of S. U is an upper bound. Then U be the supremum of S if and only if there exists some epsilon positive, then S epsilon fall in S such that U minus epsilon strictly less than S epsilon. So come to this result, that U be an upper bound of a non-empty subset S of R, then this upper bound U is said to be supremum of S if and only if necessary and sufficient condition for all epsilon positive there exists some S epsilon fall in S such that U minus epsilon strictly less than S epsilon. So how proof is done? By this way, come to the necessary argument. So first suppose that U be an upper bound of S. Let U be an upper bound of S. U be an upper bound of S. And assume supremum S equals U. Assume the first part. Supremum of S equals U. Since supremum of S equals U, it is given that epsilon is positive, then surely U minus epsilon strictly less than S. It is U minus epsilon strictly less than U, since epsilon is a positive quantity. U minus epsilon less than. U minus epsilon less than U means U is the least upper bound. U be the least upper bound. So U minus epsilon less than U means U minus epsilon is not an upper bound. U minus epsilon is not an upper bound. U minus epsilon is not an upper bound means there exists some S epsilon fall in S such that U minus epsilon strictly less than S epsilon. Okay. So what about the reverse inclusion? For reverse inclusion, let S be a non-empty subset of R. Let this given S be a non-empty subset of R. Then for all epsilon positive, there exists S epsilon fall in S such that U minus epsilon strictly less than S epsilon. This is the hypothesis. Then let V less than U. letter v less than u. Means u minus v should be positive. U minus v should be positive. Then we choose an epsilon. We choose epsilon is positive. So instead of epsilon, put u minus v. So u minus v is epsilon. Why? Because it's a positive quantity. Then, if for all epsilon positive, replace epsilon by u minus v. Then by hypothesis, then there exists some s epsilon falling as such that u minus epsilon strictly less than s epsilon. That means u minus, what is epsilon? U minus v. U minus of u minus v strictly less than s epsilon. That means u minus of u minus v means v strictly less than s epsilon. V strictly less than s epsilon means, that means v is not an upper bound of s. Not an upper bound of s. So, but is v is chosen as this way. V is selected as v less than u, but any number v is an arbitrary. So any number less than v is not an upper bound of s. That means any number less than u is not an upper bound of s. That means u be the supremum of s. That is the reverse equation. So u be the supremum of s. Agree? So this is the proof of this lemma. Now let us discuss an important result. That is, what about supremum of any union of any two sets? Supremum of union of any two sets. So the result says that letter A and B are any two bounded sets, or any two bounded subset of R. Any two bounded subset of R. Then prove that A union B is bounded. Then there is a result. Then A union B is bounded. This is the first part. And second part, also supremum of A union B. Supremum of A union B equals supremum of supremum A supremum B. This is an important result. If A and B are any two bounded subset of set of real, then we have to show that A union B is bounded, as well as supremum of A union B equals supremum of supremum A and supremum of supremum A supremum B. Similarly, infimum A union B. Infimum A union B equals infimum of infimum A infimum B. So these are two important results. So first we consider this problem is solved by using the following arguments. Since A and B are bounded, so A and B are bounded means A has an upper bound, A has a lower bound. So it is supremum and infimum are exist. Let supremum of A. Let supremum of A equals small m1 and supremum of B equals small m2. M1 and M2 are supremum of A and B respectively. Then let X fall in A. X fall in A. But A has a supremum M1. A has a supremum M1. That means if A is in a non-empty set, then the supremum means its largest element is the supremum. Okay. Its largest the set if A is a finite set or A is a finite set, then it has its largest element is the supremum. Since supremum of A equals M1 and X fall in A, that should implies X less than or equals M1. Agree. If X fall in B, then B has supremum M2, then surely X less than or equals M2. X less than or equals M1 and X less than or equals M2. Then choose M equals supremum of M1 and M2. Choose M equals supremum of M1 and M2 means supremum of supremum A supremum. Since M is the supremum of M1 and M2, so what's the conclusion? Clearly m1 less than or equals m and m2 less than or equals m. m1 less than or equals m and m2 less than or equals m. Now listen, x less than or equals m1 but m1 less than or equals m. So combine x less than or equals m1 and m1 less than or equals m. So what do you get? By the transitive property, it is x less than or equals m. So it implies x less than or equals m for all x falling a. And similarly, m2 less than or equals m, x less than or equals m2. Again by the transitive property, there is also x less than or equals m for all x falling b. Thus, we can conclude that x less than or equals m for all x falling a union b. A intersection b also, it is again x falling a union b. So x less than or equals m is any positive real, that is for all x falling a union b. So what's your conclusion? That means a union b is bounded. A union b is bounded. That is the first part. When a and b are bounded, and then a union b is also bounded. So when a and b are bounded, a union b is bounded. That is proved by this arguments. Okay. Now we have to show that what is supreme of a union b equals supreme of supreme a and supreme b. So for let capital M equals supreme of a union b. Capital M equals supreme of a union b. Then we show that capital M equals small d. Okay, we have to show that capital M equals small d. Enough. So, but supreme of a union b, what is supreme of a union b? That is m. Supreme of a union b is m, and what is small m? M, a union b is bounded for all x less than or equals m, x falling a union b. So m is an upper bound of a union b. M is an upper bound. M be the least upper bound. So what do you get? M less than or equals m. Agree? M is a upper bound of a union b, but capital M is the supreme of a union b. So capital M less than or equals small d. Now again, let the capital M be again also. Let the capital M be the supremum of a union b. Capital M be the supreme of a union b. That means when x less than or equals m, x less than or equals m for all x fallen a. X less than or equals m for all x fallen a. That means x less than or equals m or x less than or x fallen a union b means for all x fallen x less than or equals m for all x fallen a union b means x less than or equals m for all x fallen a or x less than or equals m for all x fallen b. Okay. Yes. That means, but what is x less than or equals capital M? Enough. But x less than or equals small m1. So we can conclude that m1 less than or equals m and m2 less than or equals m for all x fallen a or x fallen b. Enough. That means supremum of m1, m2 less than or equals capital. That means what is supreme of m1, m2? It is chosen as m. So m less than or equals capital. So come to these two arguments, m less than or equals m and the small m less than or equals capital M. So combines you have m equals small d. Thus supreme of a union b equals supreme of supremum a and supremum b. Agree? So come to the second part. The second part is also proved by the same argument. Infimum of a union b equals infimum of infimum a, infimum b. That's again proved by using the same arguments. So instead of yes, we can choose For how? Let a infimum of A1 instead of supreme of A, let infimum of A is small n1 and infimum of B is small n2. Okay, so let x for in A means n1 less than or equals x and n2 less than or equals x. So, but we have let a capital N is infimum of n1 and n2. Then, but then as A and B is bounded, then n less than or equals n and so on. Then proceeding like this argument, then you can show that infimum of A and B is infimum of infimum and infimum B. So this is the proof of this result. Okay, thank you.